Welcome. The title of today's notes worksheet is Parabolas Day 3. This lesson offers us an opportunity to do some applications with parabolas, do some modeling on the coordinate plane, and maybe solving for any variable that is appropriate within the particular problem. So why don't we go ahead and get started here. We'll take a look at a couple of diagrams that I pasted on your paper, and then maybe I can bring up my program, show it from a, a more dynamic perspective in just a little bit here. So here's how we're going to play it out today. I'll just pretty much read from the paper, and then you'll probably have to do a little visualization on your own if you can. So it says applications of parabolas. If a parabola is rotated about its axis of symmetry, think about it being rotated infinitely fast about its axis of symmetry, it would form a three-dimensional figure. And that three-dimensional figure is a parabolic surface called a paraboloid of revolution. That's what we're going to be taking a look at today, paraboloids of revolution. And it's useful for its reflective properties. So we're going to take a look at it really from two different perspectives. Either the paraboloid, paraboloid of revolution is going to be the source itself, or the paraboloid of revolution is going to be the collection point from an outside source. And so let's go ahead and take a look at those two perspectives on your paper. It says, if a light is placed at the focus, all the rays emanating from this source will reflect off the mirror in lines parallel to the axis of symmetry. And this principle is used in the design of searchlights, flashlights, and car headlights, etc., etc. So what we have here is the bulb placed right here at the focus, and the rays bounce off the parabolic surface and out here parallel to the axis of symmetry, kind of like that. And you can see a nice looking paraboloid of revolution in this picture right here to illustrate that. So this is where the paraboloid of revolution essentially would be the source. Here's the bulb bouncing off of it that way. Beautiful. And then let's go ahead and take a look at the next piece. Conversely, if rays of light or other signals emanate from a distant source so that they are essentially parallel, they strike the surface of the paraboloid of revolution and are reflected to a single point at the focus. This principle is used in the design of some solar energy devices, satellite dishes, telescopic mirrors, the Hubble probably being the most famous, although I'm sure it's much more intricate than something like this right here. But regardless, here's what we have. So we have the incoming light, or whatever source we're talking about, and it's coming in parallel to the axis of symmetry if it's placed right, and it bounces off our parabolic surface and goes right to the collection point here at the focus. And you can see that with this little telescope right here, bounces off the mirror right to the eyepiece, and then you can kind of see right here. Here's the focus right here, and that's where it's looking at. Kind of cool. Let me bring up my program just a second, and we'll do just the few examples that I have here. This one should be relatively short and sweet. So there we go. So I've got my Sketchpad program all keyed up here, and here are our paraboloids right here. And so let's see, here's that three-dimensional figure if you could potentially have envisioned it. So again, that would be a parabola. Think two-dimensional for a moment. A parabola being rotated about its axis of symmetry infinitely fast and forming this three-dimensional figure here. So let's go ahead and just show this in action. I think I'll do this one right here. There we go. So there's the focus. So let's do this. Here's the source, or the light or radio signal or whatever, bounces off, goes right to the focus. And then it works outward as well. Let me catch that piece just one time. So if this is the source, bounces off the parabolic mirror and bounces outward nicely right there. Okay, so I hope that reflective property from the focus kind of helps. Been obviously emphasizing the position of the focus quite a bit here over the last couple days, and obviously we'll continue to do that here today. All right, pretty awesome. Let me move into, let me go ahead and stop that piece, and let's get into our examples here. Let's just try it out. The modeling is going to be very straightforward. That's the good news with this. So here we go. Example 1. A satellite dish is shaped like a paraboloid of revolution. The signals that emanate from a satellite strike the dish and are reflected to a single point where the receiver is located. If the dish is 8 feet across at its opening and 3 feet deep at its center, at what position should the receiver be placed? All right, so here's the idea. We're going to model our paraboloid of revolution and then kind of answer the question at hand. So this is the good news piece. We've got a lot of choice in this. I have a coordinate plane. I'm just going to go ahead and throw one in there just for kicks. I want to model this paraboloid of revolution algebraically. And so I guess the idea is when I model this, I have some options. I can place it wherever I want, and I can open it in whatever direction I want. So I guess the first order of business is to talk vertex here. If we had to put the vertex anywhere we wanted on the coordinate plane, where would be the easiest point? Where would be the best spot? And I would argue probably at the vertex. I'm sorry, the origin right there. Vertex at the origin. Good. Now we also have the opportunity to open this up in whichever direction we want from there. It's up to you. Students over the years have pretty much suggested that opening it up from there would be the best course of action. And so that's, I think, what I'm going to do, at least on the board. If you want to open it differently, that's fine. But basically what we're going to do is a cross-section of this paraboloid of revolution, so a two-dimensional parabola representing the characteristics that are given in the problem. So let's read that problem again and see what we can detail in there, and then we'll go to work on modeling. So let's see, single point where the receiver is located. The dish is 8 feet across, so there's the cross-section right there, and that would be 8 feet all the way across, if you can picture that. And 3 feet deep at its center. So from there to there is 3 feet, something like that. At what position should the receiver be placed? Now, this is a satellite dish. I'm not sure if the receiver is going to be placed inside the dish or outside the dish. I don't know. But for our drawing, quite frankly, it doesn't matter. I'm just going to throw the focus wherever we want. That's where the receiver is going to be. So that's the reflective property. They're going to bounce off like this and go right to the focus, which is where the receiver wants to be placed. Okay, well, let's go ahead and start this. So I'm going to go very generic on this model and just watch what happens and how nice this is. The way I drew this here, everyone, I'm going with a parabola that is opening up. So what I know about a parabola opening up is that the y, and don't write this on your paper just yet, hold off for just a sec, but the y would be the linear term with the 4p over here, and the x minus h would be the one that's squared. So it looks something like that. The beautiful thing about this, everybody, is I have that vertex, which happens to be at 0, 0. That's our h and k, right? So I can even simplify this further. That's why I said don't write this down just yet. Let's go simpler. X minus 0 squared is just x squared. And y minus k, or y minus 0, is just y. So look how nice this model is right here. Now we can run with it. So I would argue we probably have 2 of these 3 values, and we're going to have to find the third. So let's see what we have. Well, I've got 8 feet across. We do have to be a little careful on this. But I hope you would be in agreement that I do at least have a couple points on this parabola. We've seen this before. Just be careful. I'm thinking that's a 4, 3 as opposed to 8, 3. Just, again, that's one mistake I would see on this. And that's x and y. And we're missing p. You know, I kind of drew that in there. I have no idea what p is. So let's go ahead and solve for it. So here we go, guys. I've got 4 squared, so x squared, so 4 squared right there. 4 times p times 3. And that's it. Let's go ahead and utilize it. 16 equals, kind of get a 12p right there. 16 divided by 12, that should be it. And if I do 16 divided by 12, I'm seeing this as 1 1/3. If you want to go ahead and do 16 divided by 12 on your calculator, that's fine. But I'm getting 1 1/3 as our p-value. And so that would be the situation from here. So above the vertex, that's p. By definition, vertex to focus should be going up 1 1/3 right to the receiver. So however you want to write this, just want to catch my units. But I guess I would try to be as clear as possible. It looks like 1 1/3 feet above kind of the bottom of the dish or the bottom of the vertex, or above that vertex there. Cool. You know, phrase it however you'd like. As long as your math is legitimate, we're good to go. Wow, that's great. Nice. I'm just curious if I have my program kind of laid out there. Let's see. So I have this. Here's some of the photos, by the way, just of some. These are paraboloids, and you can see some other interesting ones over here. But let's focus on the paraboloids for just a moment. Here's a good-looking satellite dish right here. If you see on this one, the receiver is located well above the dish, kind of a wide dish right there. But there's your receiver, which would be, of course, right at the focal point. So kind of cool. All right, let's bring my stuff back up there, and let's go try example 2. Now that we have this taken care of, this really shouldn't be too bad. So let's see, a radio telescope has a parabolic dish with a diameter of 100 meters. The collected radio signals are reflected to one collection point, called the focal point, being the focus of the parabola. If the focal length is 45 meters, find the depth of the dish, rounded to 1 decimal place. Okay, let's model the whole thing and then answer the question. Again, if you decide to do this a little differently than I do, it's fine. So many different ways, but I like that vertex at the origin first and foremost, so I'm going to throw a little 0, 0 in. There's going to be our H and K. I like going up. I think it's, I don't know if it's necessarily the easiest, but it's probably the one we're most familiar with. So let's see, diameter is 100 meters. So there's our cross section right there, 100 meters straight across. Focal point is 45 meters above, and again, I don't know where this is on this axis of symmetry. No idea, but that focal point is 45 meters above the vertex, so P is going to be 45. Everyone okay on that info? Good. Now what we're trying to find is this right here, the depth, the Y value. Okay, so here we go. No time like the present. X squared equals 4py. And that's what we're going to put in place. And then from there, of course, I probably have 2 pieces and need to solve for the third. Just be careful on this. I'm seeing this, what we're trying to find, I'm seeing that as a 50 as opposed to a 100. Again, just want to make sure on that. All right, let's go for it. X is 50. 50 squared, 4 times 45 times the Y. Nice. I could probably pull a little of this off. We've got 2,500 here. And 4 times 45, I'm getting 180 on that. Looks good. And obviously, guys, we'll do our division here. 2,500 divided by the 180. Oh, I have to say somewhere in between 10 and 15, but let's figure that out there. Let me bring my calculator. And so I have 2,500, and let's divide by that 180. There we go, about 13.89 feet. That would be the depth. And was this, nope, sorry, not feet. I want to be clear on my units. So 13.89 meters, give or take. Oh, that looks good. Here's what's kind of interesting. I guess my drawing was not perfect. Again, I wasn't sure about that focal length, but if the focal length is 45 and the depth of the dish is only just under 14, I guess this receiver, is that what it is here, or receiver? Yeah, is going to be all the way up here. So again, I drew it incorrectly, but I obviously still did the math correctly there. Didn't matter when all was said and done. And I guess that kind of looks, sorry for bringing this up again, but yeah, it kind of looks like this piece right here. So notice the depth is quite a bit smaller than the focal length. Yeah, kind of cool. All right. So those two, nice and straightforward in terms of paraboloids of revolution. You're sketching it however you'd like, to be honest. And I would argue in these 3 pieces, X, P, and Y, you'll have 2. You'll have to find the third. Let's go do one more. So example 3. Now this one, I think we're going to be a little more restricted. So let's see how we want to do this. An arch in a memorial park having a parabolic shape has a height of 25 feet and a base width of 30 feet. Find an equation which models this shape using the x-axis to represent the ground. Determine the height of the arch 4 feet from the end, and we'll even go focus and directrix one last time just for kicks. Okay, so coordinate plane. I've seen students do parabolas two different ways with this. Ones that open down, again, not too much choice, but you know, I see students open it two different ways. So that is a perfectly legitimate one. Or I've also seen students over the years focus more on the first quadrant and do something like this. Now either way would work, of course, as long as your numbers are correct. You would get the same answer in the end. Now obviously I can only go with one of those two. I'm going to probably do that first one right over there, where I have my parabolic arch and just the x-axis representing the ground, so kind of like that. Okay, so that's what I'm going to look at, and let's see what this arch looks like here. Base width is 30, so that's 30 all the way across from there to there. And a height of 25, so that would be from here to here. There's 25. All right, not too bad. Let's see if we can model a few things, get a couple points in place. I have those 2 points. I only need one of them. Hoping you agree that that would be 15 and 0. Does that sound right? Because it's 30 all the way across. And the way I at least put it right in the middle there, having that y-axis kind of be our axis of symmetry. So I'm thinking 15 and 0 there should suffice. And then here's the key right up there. We've done this before. I like that as a 0.25. And that 0.25 is our h and k. So unlike the last two, here's the one dilemma. Unlike the last two, I couldn't throw the vertex right at the origin. And I don't think I would necessarily for a parabola opening down. I don't know. I just, especially when we're trying to talk about this situation, let's keep everything above ground. Okay, but I think we're ready. So a parabola that opens down, let's start with that piece. Really good solidifying of these ideas. If it's opening down, it's 4p, and if it's opening down, it's the y that's the linear, so the y is next to it. Now we've been talking with this piece for 3 days. And it's the x that's squared, and so that is what I'm looking at right there. I'm going to model this, so I have a feeling I'm going to need my coefficient out in front. I'm going to get p and then get my 4p, so we'll take care of that piece. All right, let's fill in what we know. X is 15. Put that into the mix if you would. H is 0. Square that piece and that piece only. Okay, then I have my 4 times the p, and then let's do y minus k, so in this case 0 minus 25. Okay, we're looking good. Everything should work out nicely from here. 15 squared is 225. I've got my 4 times p times negative 25. Looks good. See how much I can do in my head here. I've got 225 on this side. You do too. 4 times negative 25 is negative 100. So it did talk about the position of the focus and directrix. We'll go ahead and put that in place. But I think it'll come from here. So 225 divided by negative 100. I'm getting just nice and simple there. How does negative 2.25 sound? And we'll go ahead and sketch that in just a minute. But that's a good p-value. I'll utilize that. But more important, I think it allows us to write our equation. So let's go ahead and do that. So now we go x minus h squared, or x minus 0 squared. Right? So x minus 0 squared is going to be this. My 4 times p, so let's put that in place, everyone. 4 times this, if you did it on your calculator, I'm getting 4 times p, or 4 times negative 2.25, to be negative 9. And then just watch your model, make sure everything is perfectly legitimate and correlates well with your drawing. K is 25, and so y minus 25. Wow, take a look at that, make sure it matches up. Make sure you agree on everything before moving forward. But now this model right here is for the infinite number of points on this parabolic arch. Now let's finally answer this question. Determine the height of the arch 4 feet. Ooh, I like this. 4 feet from the end. So let's go ahead and see. Here's where we are, 4 feet from the end. Either end would work. I'm going to go from this end just to stay positive. let's go 4 feet from the end, and we want to know the height. So from here to here is going to be 4. And so the question is that I have for you is, what is the actual x value? It's not 4. And it looks like, just the way I see it, it's got to be 11, right? Because it was 15 from here to here. I'm coming in 4 from that 15, so that's what I'm looking at. X is going to be 11, and the y is the unknown, and that's what we'll solve. All right, let's run the calculation. 11 squared, -9, y minus 25. Just good algebra. You've been working on this stuff for years. I'm going to just come up here a little bit and get 121, and then equals -9 times y minus 25. Hey guys, I see this in 2 steps. So if we're going to solve for the variable, what do you say we undo the multiplication of -9? So let's take 121, divide by -9, and then I'll add 25. I'm going to do that in one shot if that's all right with you. And let's see what we end up getting. Should click. It should work out nicely. 121, divide by the -9, and then add that 25. And that's what I'm getting. About 11 and change there. Let's see. So about 11.56. And I guess this would be feet. Wow, super. Nice. Anything else we want to do with this? I don't know. Do we want to state the focus and directrix? Yeah, why not? Just good quick review. Good way to wrap up. It's a short lesson anyway. So I did this. I answered the question here. Determine the height of the arch 4 feet from the end. The height is going to be just over 11.5 feet. All right. Now, if there is that focus and directrix, again, that sort of generates the shape of the parabola there geometrically. Let's see. We already found P, which was -2.25. So are you okay coming down 2.25? And that would be our focus. And then going up 2.25 and having our directrix, something like that. I'm hoping. I mean, I'll go ahead and put both up here, and if you want to jot that in, that would be great. If I went down from the 25, 2.25, I'm getting 22.75 on that. Does that sound right? Take 25, subtract that 2.25. There you go. There would be your theoretical focus. And then the directrix, horizontal in nature, of course. So you know the directrix is going to be a y equals situation. And I would go 2.25 up. So how does 27.25 sound to you? Yeah, kind of cool. Again, nothing more than just a good review on all that stuff. Obviously, is that a necessity for a problem like this? No. But I like the modeling. It's great stuff. All right, so some good applications to focus on here. Let me know how I can assist you. But Parabolas sort of now ends the 3-day set. The geometry, the algebra, and the applications all put together pretty well. Cool. All right, well, we'll stop right there.